Welcome all to this 13th lecture of Principles of Statistics. As I mentioned in the last lecture, in this one we're going to concentrate on the so-called Bernstein-von Mises theorem, which is essentially the ultimate result that will justify, from a frequency point of view, the Bayesian methodology. So let's get started with this, and let me also apologize for the delay in posting this lecture. So let's get straight to it. So this is theorem now. So this is theorem 1 from this section. And so we're going to be in the context of the asymptotic normality of MLE, right? So that's the context that we expect because we want to prove something of that kind, and we'll see what exactly now. So let me then consider, so for a statistical model, for a statistical model of theta in some capital theta, and data as in the in this MLE, asymptotic MLE data result. So both of them as in theorem 4 from section 2. Then we're going to consider a prior, right? So that's the main difference that we're going to need in the statement, at least in the beginning of it. So consider a prior. This is a distribution, I remind you, pi. And so what condition do we need? Well, I anticipated a bit what we needed. So that is continuous and okay, so that has a continuous density, which with some abusive notation we're also going to call pi, and this is well, it has to be continuous only around so only at the theta naught. Okay, in fact it can be discrete, and I will make a remark after the theorem. But let's focus on this case. So we wanted to have a density at this point, and such that the density at this theta naught is greater than 0. Yeah, so this is something I anticipated in the previous lecture. So let me write pi n for I guess so I want this to be, so for the, let's say for the, let this be the density of the posterior okay, and I'm sort of using these, or the notation of pi interchangeably with whether it is a density or a measure, but it should be clear from the context what I am using. So this guy, right, and this is of course on capital theta, and let also, just for conciseness, write phi n, okay, and this is small case phi n, or lowercase phi n, be the density of a normal distribution that is centered around the MLE, okay, and that has variance equal to 1 over n of the inverse of the Fisher information matrix. Okay, and it's important, is that this has to be centered at the theta naught. Okay, so remember I've said that the data is as in theorem 2.4, and there we had this frequentist interpretation that the data was generated by one of the elements of this statistical model, and we call the parameter of that element theta naught. Okay, okay, so the density of, okay, so maybe this is a bit better to say of a normal distribution or variable. Okay, So then what do we have as the statement? Well, then, what we get is essentially L1 convergence of the posterior density, okay, to this phi n. Okay, so this respect the theta, and so this goes to 0. And now the question is, in what sense? Well, this is in the p theta naught capital N, almost surely. Yeah. Okay, so this means that if we look at this measure of p theta naught, of this infinite product measure corresponding to these IID random variables generated by this p theta naught, then for a set of probability 1, we will get the convergence in L1. Okay. Okay, so that's a very strong result, yeah, and this holds, as you see, for any finite dimension. So, but when you go to infinite dimensions, the game changes completely, and this is this is active research, even though it's been about nearly 10 years that there is we now have some good understanding for infinite dimensions. Yeah. Okay. So let's give some sort of proof. So let me maybe write it like this, or prove in this sense, because so the I guess the let's say a full proof requires Lecan theory. Okay, and that's a bit too advanced for this course, and even though we could cover it, it's just it may take a bit too much time for just one result. So a full proof requires Lecan theory, and by the way, so you can see these things in the Advan Abad book, but there is a good proof, there are good notes essentially from Richard Nicol, professor in Stats Lab, from a 2012 Part 3 course called Statistical Theory. So if you're interested in seeing this proof, just search for that online. And if you cannot find it, then just drop me an email and I'll ask Richard whether he minds me putting it on my website, uploading it to my website. Okay, so we cannot really, give it in full generality. And actually, we're going to be restricted to a very particular case that we've already looked at, in previous lecture. And so we're going to consider only the toy case of a normal distribution, with unknown mean but known variance. So we're going to consider only, as I just said, the case in which this x given theta is a normal distribution with mean theta and variance 1, and because we're in this Bayesian framework, then the theta requires a prior, and this is going to be given by a standard normal. Yeah. Okay, so if we consider this, then let's make. Okay, so we want to show this. Okay, so let me first of all make a okay. So let me make a claim. Okay, so let's start with a claim. So claim. So we're going to claim that the left-hand side. So maybe let's call this star. So star is going to be equal to 2 times. So 2 times the integral over Rp of the positive part of these guys. Yeah, and so this is a very common sort of trick or a starting point for some proofs of this kind, and it shouldn't be hard to justify. So, and this is because, so indeed, if you take a look at the value of let's say, so if we take the integral of pi n minus phi n, and let me just drop the thetas, then of course, this is going to be 1 minus 1 because these are densities, and so this is going to be 0. So what we get is that, so really, if we look at, the left-hand side here, so this guy is just simply the sum of the positive part and the negative part, right? So it means this, which is just equivalent to saying that the negative part is minus the positive part, and also, so maybe, yeah, okay, so then star, which is the absolute value, okay, so this is the absolute value. The absolute value is just no more than the positive part minus the negative part, right? And so then what we're left with is just 2 times the positive part. Yeah? So this is more like probability measure standard trick, yeah. But not even probability measure. It's just trivial sort of arithmetic calculation. Yeah. Okay. So so we get this, and then how can we rewrite then the right-hand side here? So maybe let's call this double star. So double star here can be written. So then, okay. So let's now say, so since we know that the phi n hat is greater than 0 actually on the whole of R, okay, and this is because it is density of a normal distribution. What we can do is we can write this double star as simply, we can take out phi n hat, and so this is the integral over Rp of, in this case, it would be, so let me, maybe I wanted to write, sorry, so actually, indeed, okay, so I've written this the wrong way around, but shouldn't be an issue. Okay, so let's, okay, this may be an issue. Okay, so let me just for, it's not an issue, but let's just for cleanliness, write, okay, so let me write maybe, so the statement, of course, is in terms of an absolute value, so we can swap the order of the 2 guys, and that wouldn't change anything. So what I want to claim is that this is 2 times the phi n hat. Okay, so this is just the same thing, yeah. Okay, so what I want to say here is that, so let me maybe correct this a bit, so phi n, and then phi n hat minus pi n, and then this means that we can write here the pi n as well. Okay, so then so then what we get is that this is 1 minus pi n over the phi n hat, so of course a theta, and this is the positive part, and we've taken out this guy, yep, d theta, yep. Okay, so that's sort of trivial stuff, and so maybe, okay, so this is where really we can use, so far we haven't really used much about the normality. We have used this positivity, but that's not very, very particular just to normal. So let's now really exploit the normality by writing out the actual expression that we get in there. And so this is going to be, okay, so recall, okay, so, or maybe note that phi n is density of, so in this case, a normal distribution with an MLE, yeah, but the MLE is just simply written by the, so it's simply given by the sample average, and the variance, I remind you, the one that we get is, well, yeah, the variance or the optimal variance, this Fisher inverse is going to be 1, and so we get this 1 over n, yeah, as a result. And the pi n is also the density, and now of a normal distribution, but there was a little, so we had we had to have an n+1 in the denominator, and so we multiply by n and divide by n+1, n+1, and there was a similar thing going on in the variance. Yeah. Okay. So given this, what we get is that so the right hand side, so maybe let's say double star, okay, and the double star now of course means the right hand side up here, can be written okay, yeah, so it can be written as follows. Yeah, so this guy is just given by 2 times the integral over Rp of 1 minus, and then we get this sort of so let me maybe, what should I write? Okay, so let me write it out. So 1 over 2 pi divided by n+1, and this is to, of course, 1/2 only, and then we have the exponential of n+1 halves, and we also get theta, and we can add and subtract a theta and hat, and of course we get this guy here. Yeah. Okay, so yeah, because that was the mean. Yeah, so that was that in there. Yeah, that was the, as in the posterior mean. Yeah. Okay, so we get this. Okay, it's not gonna fit. Okay, this is the positive part. Excuse me, sorry. I know I said I would try to write a bit cleaner, and I'm not going to, at least in this bit. Okay. So then we can divide this by this 1/2, and we get this n halves theta minus theta n hat. So then let me now talk about the, what we are, so what we're missing here is just to integrate basically with respect to this guy, and this guy is going to be the same as, what we get in the denominator in the previous line. Okay. Okay, so then given this, we can change variables. So let v be so let v be square root of n of theta minus theta n hat. So what we want is the guy that we've got here, and so of course this means that dv with respect to theta is going to be no more than square root of n. Okay, and so we get now that the previous line can be written simply as okay, so that's 2 times integral over r. Actually, I'm writing rp, but of course it just this is p equal 1. Yeah. The whole thing. Yeah, so of course, I'm considering this, so this is p equal 1. Yeah. That's sort of obvious. So I can, I guess, yeah, okay, so let's continue now on R, just for clarity. So what we get here after the change of variables is just simply following quantity. So this is n+1 divided by n, and the exponential of n+1 over 2 times n. So that's something that is just a bit greater than 1/2, and we get this v plus square root of n theta n hat minus theta n bar. Okay, which is, by the way, a quantity we've seen already, and I will therefore use something we've seen. Okay, and then we get this with the square. Yeah, and this is closed with that, and we get the exponential of the halves. Yeah, dv, and this is now over square root of the 2 pi. Yeah. Okay, so what can we say here? Well, there is something that that we showed, and this is what I was referring to. So maybe let's recall. Recall the following. So recall that the square root of n of this theta n hat minus theta n bar, goes to 0 almost surely under this theta naught n. Okay, so this we saw, I think, in the last lecture, if not the previous one, and then of course, and so does n plus 1 over n. Yeah, that's trivial. Yeah. Sorry, and okay. What I want to say is that n plus 1 over n goes to 1. Goes to 1 also almost surely, which is rather silly to say. Okay, so what does this mean? Well, it means that the positive part, this positive part, will converge to 0 for every theta fixed. Okay. On an event set of events, a n of probability 1, right? Okay, so that's just by the definition of convergence almost surely of these two guys, and then you can check that if you fix the theta, you get this. And then additionally, we also get, so in addition, we also get that this guy is bounded by 1, okay, and actually, of course, bounded by 0 below. So bounded by 1 is, of course, obvious because the ratio that we've got there is just it's non-negative, okay. Okay, and so so this means that actually, because this guy is integrable, then so is the product of these two things, and we can use the dominated convergence theorem, which is in the handout, implies that, or justifies or shows that do we need something else? Well, okay, so let's say justifies that. Okay, I'm a bit worried about phrasing it in this way simply because, okay, so what I want to say here, of course, is that this guy tends to 0. Yeah, the whole integral tends to 0. Now, it is true that the positive part tends to 0 for every theta, and it's also true that this positive part is uniformly bounded over the thetas, and so it means that we can basically use the dominated convergence theorem, but this guy, so the integrator here, will depend on n, so we also need to take care of that. Okay, so this is why I'm sort of a bit reluctant to write it like this. So I think there is more to say here. I mean, I could skip so I am indeed going to skip the step a bit, but I do want to give you a bit more details about it. So so in addition, this happens, and we also have that V. So V is, I remind you, is this guy here. Then V is actually converging, so it converges to a normal distribution. Remember, this is the MLE, and so this is actually OP theta naught and bounded. Yeah. Okay. And so if it is bounded, then you can essentially argue that, so it's bounded in probability, then you can argue essentially, so maybe think what this implies. Okay, so let's say, okay, so maybe what you need to think about is that therefore, I think, okay, I will just give you now a little comment on this. The dominated convergence theorem justifies that, the double star converges to zero almost surely under this measure. Yeah. Okay, and this completes the proof. Now, the little comment I want to make about this is that this type of, so I'm not, I'm certainly, so sort of answering again the question I got last week. So I'm not going to ask for you to prove the Bernstein von Mises in the exam. Yeah. Even, I mean, just for this special case that we're considering. But it is true that this kind of arguments that we need here are going to, arguments that you're definitely going to have to use in the example sheets. And I think the exam is a bit more in line with the example sheets rather than, with the proof of the Bernstein von Mises theorem. And so really it is good practice for you to think about these things, yeah, how to argue this, yeah. Okay, so let's move on and just make a couple of remarks, and then we'll really talk about inference, how this justifies inference. Okay, so let's maybe make some remarks. So we have one here that this is something I already sort of mentioned. So a discrete, and this is of course for pi version, exists. Okay, and then the second thing is that, so we took, so we centered this guy, which is so we centered that guy, which is actually, what we sort of consider to be the limit, which is of course not the limit because it depends on n. But, the approximation, or, well, it's not really, yeah, okay. So the approximation, we centered it around the MLE, but we could also, there are many occasions in which, well, maybe not many occasions, but there are occasions, and especially in more complex models, in which the MLE is not very clearly computable, but maybe you can get hold of the mean of the posterior distribution. And this is not really because the posterior is any easier than the likelihood, because it certainly isn't. But it's more because it gives you a very principled way of having a fully Bayesian construction of the inferential procedures, right? So if you can, if you plug in here the mean, the Bayesian, the posterior mean, then everything is in terms of the posterior, and you don't need to talk about MLE even. Yeah. So that's just that's the comment I wanted to make, and so it's just to say that this guy in this guy can be replaced. So I will try be replaced by this. Okay, and this, of course, because we have this. Well, I mean, it partly is because we have this almost sure convergence of this guy. But yeah, the square root of n times the difference between these two guys. Yeah. Okay, so how does this translate into inferential procedures or a justification of them? So let's now, okay, so let's maybe sort of make a little break there and say that assuming the Bernstein von Mises theorem, we can justify that the credible set given by, so the credible set given by, that I think I spoke about in the last lecture, which is this set of thetas that are away from the MLE. Again, we could have here the posterior mean, but let's just stick to this. So this difference is no more than Rn over square root of n, where the Rn is really the key thing here. So where Rn, okay, so where Rn is such that, so it's just any, such that the Cn has mass 1 minus alpha, under the posterior distribution. Yeah? And this is for, of course, alpha between 0 and 1, so that's the usual thing. Okay, and what we want to say is that this Cn is an asymptotic level 1 minus alpha confidence interval. Or in this case, well, we are in RP again, we're back to RP, so confidence set. Yeah. Okay, so, and okay, so maybe to say, can also, or again, can replace theta MLE or n, okay, so it doesn't matter, I'm using them interchangeably, by this guy, yeah, by posterior. Yeah. Okay, and this is in the example sheet, yes, sorry. So, all right, so let's see how we can justify this, okay? So let's start by looking at what we are interested in, right? So what we want to look at is the probability when the theta naught is the true, is the parameter generating the data. So we wish to look at the probability of, under that, of the theta naught being in Cn, right? And this is, of course, just simply the same as, the theta MLE minus theta naught less or equal than this Rn. Okay, over square root of n. Okay, so now I remind you that Rn is really the key here. Okay, so Rn is key. Okay, and because the rest we understand sort of perfectly well, right? And so this really reminds us of the usual confidence sets for the MLE, right? So except for the fact that the Rn should be the Z alpha that we had, right? So then let's just, so ideally, or maybe would be great, or ideally, yeah, would be great if Rn were approximately this Z alpha, which I'm now going to write in this form, and I will define this capital Phi just now. So where capital Phi we can define as the integral from minus t to t of phi of theta d theta, okay, and where this lowercase phi is going to be the density of a normal distribution so normal distribution that is centered, and it has variance Fisher inverse, or inverse of Fisher information. Yeah? And this is, of course, this is a variable. Yeah? Variable. Okay, so this is the right quantity that we wanted, because the Z alpha was exactly this value for this distribution here. Yeah. Okay, so let's then try to prove something like this. Yeah, so we need some sort of convergence for this guy. For the Rn to this value, that would be ideal, right? And that's exactly what we're going to show. And so then let's note that because of this guy being this capital Pi being this sort of nearly a distribution function of this normal distribution, then we can invert it. Yeah, so it is invertible. So if you're not convinced, just think about it a bit. So it's invertible. So it's invertible, and so this thing is -1, evaluated at this other thing, so Rn should be equal to Rn. Yeah, so we know that. And let's now sort of say, well, and since this guy is continuous, and by the continuous mapping theorem, what we get is that it suffices, or it will suffice. So let me just write it in this way so that I still talk about this. So it will suffice to show, or to have that phi n at Rn converges to 1 minus alpha. Yeah, because if we can show that, then because the capital Phi is going to be continuous, and we have this inverse, and actually this is strictly monotone, and so you can argue that the inverse is also continuous. And so if you have that the inverse is continuous, then of course you can look at the limit of the argument, and the argument, I'm talking about this guy here. So we can say therefore that this 1 minus alpha, so this will convert to 1 minus alpha, and so this guy will be the right quantity, yeah, or it will convert to the Z alpha. Yeah, but I will talk about this sufficiency in a sec. So let's just assume that it is sufficient to show this, and let's show this. So how do we do so? Well, let's just write it out. So but this guy is no more than so I remind you, this is just the expression that we had above of the phi at theta d theta, and we can change variables here. So let's take just as before. If we write the v to be so some v to be square root of n of of the let me just think about this. So yes, so we get just the same as before. So the derivative is just the square root of n. Then what we have is that we can write this as the integral over Cn of the phi n hat. Yeah. Yeah. Okay. This phi n hat is from the previous proof, yeah? From the BDM proof. So it's the same, yes, as that. Yeah. Okay. So given that we've got this, so it has absorbed basically the square root of n of the change variable. So you should take a look at this and be convinced by it. So we can write now this as the same quantity with this guy minus the density of the posterior. Let me just avoid the thetas, and we can also add the posterior, and remember I'm abusing notation by writing the law or the distribution and the density with the same notation, so this pi n, so maybe actually just so that I don't abuse notation, we can write it like this. And yeah, so this is 1 minus alpha, right? And if we have the Bernstein-von Mises theorem, then of course this guy, we can, so by Bernstein-von Mises, the absolute value of all this guy is less or equal than the integral of the, well, actually more than, so even just on the whole of R. And in this case, RP, I think we're considering now. So, no, we're still considering R. Yes, okay, so we're considering R, excuse me. Yes, right, doesn't matter. Of course we are. Okay, so then this is going to be less or equal than the absolute value of the difference of the two guys, and that by the Bernstein-von Mises, this converges to 0, in this, okay, so P theta naught, almost surely, yeah. And so that's great because, we have this convergence that we were looking for, and so this guy actually converges very strongly to to 1 minus alpha. Yeah? So this is this probability. Okay, and let me just say a few words about this sufficiency that I was talking about. So this is sufficient because by Slutsky and also by the fact that this quantity is distinct from 0, then we have that this, and why am I writing this? We're making it sense in a sec. Okay, so this times the theta n hat minus theta naught will converge, of course, in distribution to a normal with 0 and I minus 1 theta naught. Okay, and so then what we get is that the guy we were interested in, which is this guy here, can be simply written as the probability and the theta naught and of this guy precisely. So this is why I was writing it, and this is the absolute value of this guy, of course, less or equal than this. Yeah, 1 minus alpha. Okay. And so by the convergence in distribution, and because we're looking at these continuous random variables, then we'll get precisely this converges to this capital theta evaluated at the inverse at 1 minus alpha, and so this of course will be exactly 1 minus alpha. Yeah. And this shows the result. Okay, so I hope you enjoyed this lecture, and hope to see you again very soon next week.